Now, teachers often start teaching chemistry with uncertainty propagation, and if you have like a 30% dropout out of chemistry, another way to do it would be to start with this. So don't be too scared, because they have actually made it a little easier. So you don't have to put this thing together yourself. You just have to understand it and maybe answer some questions about it. Okay, so basically this is just Hess's law, just showing you can do basically anything with Hess's law. And so it's very difficult to grab like a solid ionic compound like sodium chloride and just burn it and work out what the lattice enthalpy is, because that is extremely dangerous and it's a high amount of energy, and it gives off there'd be so much heat, we wouldn't have the instrumentation or the possibility to do it. But we do have all the other things. So ionization energy, you can even do in the lab. And there's other ones that we've got calculated. So we don't have to do something so dangerous. So what we're trying to do here is determine the lattice enthalpy. And so we're going to have to go through all of these little bits and pieces so you know what they all are. And just as a side note, it's always lattice dissociation energy and not lattice formation energy. Enthalpy of formation, as you know already, is standard states going to a compound. Enthalpy of formation, lattice formation enthalpy is gaseous anions and cations going to the solid. So that's different. And we're not doing that. We're doing lattice dissociation. So the lattice not going to the standard states, but going to the gaseous anions and cations, which, as you can imagine, is extremely dangerous. And I'm not even sure if that's possible unless it's in a plasma state or a high explosion. Okay, because normally in the gaseous state you won't have them in the cations, you won't have them highly charged as well. If it wasn't deadly enough to have sodium metal blow up and chlorine gas kill you as a World War I gas, let's put them in the ion state. Let's go mad. Okay, so that's what we're trying to do. So first of all, enthalpy of formation. We did this one in the last one, so hopefully that's still fresh in your mind. So standard states to the compound. We have enthalpy of atomization. This one's definitely a new one. So we're trying to get them into the gaseous state. So that there is a half of that value going to the gaseous state. So make sure you know exactly what's going on here, because you may have to halve it if it's just an x2 to 2x's. And then that's not what you want. You'll have to halve both sides. Okay, so just double check your values on that. This is the monovalent divalent in your syllabus. So if you may have to take more than one electron off to get it into the cation state. So that's ionization energy, which we've covered before. The amount of energy to remove 1 mole of electrons from 1 mole of atoms in the gaseous phase. It's all in molar proportions. Electron affinity, may have to go back a little bit to the other topics to recall that one. So currently, enthalpy of atomization is the only new one. These ones are all review. Okay, so the energy that required to take 1 mole of electrons to 1 mole of atoms in the gaseous phase. Moving on, lattice enthalpy. So this is the one we're talking about that we are dissociating. So we're taking this stuff and turning it into gaseous cations and anions. Okay, so gaseous ions. And that's it. So just a review as well for bonding. So having a large charge and a small size will give you a greater lattice enthalpy. You can see that's I've got a large charge, and if we're going up, this one will be the smallest size here. So that's the best combo. All right, so that's review as well. And then this is just a large ion with the same charge. So this one won't have as great a lattice enthalpy. So you should be able to predict as well and double check your answers based on that. So here we go. So it's put together, and you don't have to put it together, but let's follow it through. So we have sodium solid and chlorine gas. So first of all, we have to turn it into gaseous atoms. So enthalpy of atomization. So you have to put in this much energy to get this to go from solid to a gas. All right, now the chlorine's already as a gas. All right, but the next thing we're doing is atomizing it. So we have to split it up from being a diatomic to just by itself. All right, so we've got to put a little bit of energy in for that as well. And now, so we've got enthalpy of atomizations both for solid and for the gas is required because the gases are usually diatomic. We won't be doing noble gases, but all the rest are diatomic. And then the next thing we need to turn them into ions. So we'll start with the sodium because it's easier because we do a cycle. It's going to go down and it'll mess it all up. So do the ionization. Well, you don't have to do it now. We used to in the past, but they'll do it for you and you have to answer questions or fill in gaps. So the ionization energy is taking off an ion, so a bit more added energy. And so that's we're still breaking, increasing entropy and breaking. So we're putting all this energy in, and now we're getting an electron added to the chlorine, so it's going to go down. So that's like a formation of a bond releasing energy. And so that's how much energy it is to get the electron to join to the chlorine. So now we're done. We've got the atoms by themselves. We've got the elements atomized and ionized and in a gaseous form. So what's left? So we're trying to go from the lattice. So we know the formation. So elements in their standard states of the compound is here. All right, that's a release of energy because that's forming a bond. And then all we have to do is add all these up together. And there we go, we're finished. We've got sodium chloride to the gaseous atoms. And we didn't even have to do an extremely impossible, risky experiment in the lab. Okay, so that one there is added all up is 786. So that's how much energy it would take to burn sodium chloride into poisonous, well, that's poisonous and deadly and going to kill you right there, actually. All right, now you just keep throwing more energy in it. Who knows what that is? Run away as fast as you can if you see that. Okay, so you're not going to do it in the lab. So just put in all the numbers down. That's what we got. So you rearrange that. So it's this minus that. And that's how you get the number. Okay, so you just have to recognize that. Just picture it in your head or draw it out for each one if you don't understand it. And there will be do some practice questions, of course, and even go ahead because really it's an application. Just do the whole thing yourself, just so you know you've mastered it. Even though they won't ask you that in the test, it's the best way to make sure you've got full control of it all. If you can do that, you should be able to answer the little bits and pieces from other places. And just an idea of how useful it is. Once you do your redox thing, the question sometimes get asked is why is not reactivity tables and standard reaction tables correct? And I couldn't find anything on the internet, so I sort of had to put this together myself. You can do a Born-Haber cycle to work out all the reactions that are going on with reduction potential tables, and that'll put them in the correct order and tell you why metal reactivity tables are different to reduction potential tables, if you're curious. Okay, so as you probably realize now, you can do anything with Hess's law. Probably don't need to do chemistry anymore. We just do Hess all day. Okay, thank you.